Hello and welcome to my talk about in-memory apps with MicroStream. My name is Florian. I'm one of the co-founders of the company behind the project, and today I will show you how to start coding with MicroStream, the basic blocks and how the key functionalities work. And first of all, a bit of the rationale, the idea behind the project. Alright, some legal stuff we have to go through. And here are the key points, the idea behind how to install or set up MicroStream in your project, how to start it up and provide a configuration. Then the loading of data and what about lazy and eager loading. Of course, storing data, and then some customization topics, for example, custom type handlers. I will explain what's about this stuff later on, and you see in the code how you handle class changes if you update your classes over the life cycle of the application, and last but not least backup and housekeeping, and of course the move to the Eclipse Foundation. So the idea behind MicroStream is pretty simple. So in a default way to add persistence to your Java application, you always have to use a third-party service like databases and stuff, and the key thing behind it is the complexity in my eyes. You have two different data models, you have tables, graphs, key values and so on, and it's never compatible with an object model in a object-oriented language like Java is. And that's the key point where the complexity comes in, and the performance losses as well, because if you just query a database, it's fast, but then the object mapper has to create object out of this data, and that's the slow point. Even if the data is cached, the object has to be created anew every single time you query stuff from the cache or from the live database. And that's one of the drawbacks of the current application with databases. So and it adds, of course, a highly complex architecture. You add caches, you have cache hits and misses, and distributed cache if the application grows, and then the Hibernate sessions outdated, you have to rehydrate the objects again, and so on. It's a humongous source of error, and you really need experienced developers or specialists to create database applications successfully. So MicroStream pretty much replaces the JPA layer, and it's a unique storage technology apart from, or uniquely different from the current databases, because the object graph will be stored natively, meaning the objects are converted to a binary form, like the JVM keeps the data in memory. So no conversion is needed anymore, and so you only have to create and design one data model, your Java object graph, and that's it. And that's a key difference to database systems, and it feels like more like a native Java function for storing data. Like I said, only one data structure, and there's no more impedance mismatch or mapping, no more loss of performance through mapping, and it makes a pure in-memory computing paradigm possible. So you don't have to use SQL anymore to query your data and so on, just pure Java. MicroStream adds the persistence to your application, and you can concentrate on the application itself with a lot less technical detail in the background. Now keep in mind that that's a paradigm change of some sort. The source of truth, if you use a database, is always the database itself, not the application. MicroStream is not a third-party service, it's just a Java library which runs inside your application, so the source of truth is your application itself. And that's a key point to remember. So, like I said, it's just a Java library available in Maven Central, of course, and just add your dependency to the project and you're good to go. Current version of MicroStream is 8.1. Version 8 will be the last one of MicroStream because of the move to Eclipse Foundation, but more to that later on. But that's a current stable version of the project. To fire up a storage, just call one of the start methods of the embedded storage type, and this storage manager is the connection between your object graph and the storage itself, and handles all the key points like storing, loading, and so on. And most of the time we will work with this embedded storage manager type. And the lifecycle end, of course, is a shutdown method, and this is the most simple way, the most simple example to create a storage. What the start does, it will look up the connected storage. If there is any data, the object graph will be automatically restored in memory. If not, an empty storage manager gets started. Alright. Of course, you can define more parameters. You can hand over a root object, which should be used as the storage root. And the simple local storage can use a local path where the storage should be kept on a local disk. You can configure pretty much anything as a storage target which takes blobs. So blob stores in a cloud, AWS S3 for example, or any other blob storage in a cloud, local disk, any service like Kafka or Pulsar is supported. Pretty much any system which takes blobs can be used as a storage target for the binary representation of your objects. But for the most common cases, this simple start method will suffice. So from a detailed customization, you can utilize the foundation types we offer. It's basically a factory type with a builder pattern. It holds and creates on demand all the parts that form an embedded storage manager. So this is the most low-level configuration style. You can provide different implementations of any single aspect of the engine. You can the engine itself is an interface-based architecture, and you can exchange every single detail if you like, if you have to, and provide different or custom implementations of these parts. And this is done by the Embedded Storage Foundation, and there you can inject all your custom objects if you have to or if you like to. For external or more higher level property-based configuration, we have a separate dependency, and the configuration is based on properties, and the underlying classes will be generated in the background. Like you can see, the corresponding storage foundation can be created, and the storage manager, like you see. Like I said, it's a setter-based stuff, and this can be fed from outside, from external configuration sources as well, like XML files or property-based stuff. And of course, it's needed for different environments like dev, prod, and test, and so on. Current configuration parsers we are offering support XML, INI, YAML, and JSON. But based on this configuration layer, we have a lot of integrations into different frameworks like Micronaut or Spring Boot or Helidon, and these will connect to the configuration part of this framework. So if you use Spring Boot, for example, you have your application property files or application YAML file, and the MicroStream config layer will read the properties out of the underlying framework. So you don't have to mix up the stuff. Alright, so now the storage manager is set up and configured, and now we can load and store data already. So MicroStream itself, the persistent object graph has what we call root instance. It's the first point from where on the persistence begins, meaning everything which is reachable from this object instance can be kept persistent by MicroStream. That's the root instance of this graph. And the storage root method will deliver this instance. In this case, we'll see it's checked if there is an existing root after startup. If not, a default root is created and stored, though the basic setup of an empty database, and afterwards you can retrieve the root by just calling the root method and you're good to go. If an existing storage exists on startup, so root is not null, the complete eagerly loaded instance of this root object will be restored in memory automatically without any further stuff you have to call, because everything which you define not as lazy loaded will be loaded eagerly into memory at startup. And there, of course, you have to keep in mind how much you want to load initially at the start of the application, what data is needed. We say if you define a lot of lazy loading points after the root object, it's the most or the best way, because then the startup will become quick, of course, and you can access the different branches of the subgraphs with lazy loading on demand. So, but you have a lot of memory, of course, and you need all of your data in memory as hot data, then just load it all eagerly and you're good to go. So what about lazy loading? Let's say we have a business application which keeps business years, and the business year itself has turnovers and will be kept in this map of the business application. So if you have a lot of data, this approach could be a problem, because during initialization the root instance would be loaded. From there it's hash map with all business years and all turnovers. So let's say we have a company which exists for 20 years, a few million sales annually. It makes about 40, 50 or 100 million sales objects which would be loaded at startup time. And if you have not enough memory, yeah, you're in trouble. So we don't want it that way. So we just didn't partition our model to load it everything anyway at startup time. And it would be nice if you could just add a simple lazy to the turnover list to load it lazily, and that's just how it works. Just wrap a lazy definition around the list, and from there on this list will be loaded on demand if you say MicroStream should do so, and that's all you have to do. So how do you access the content of this lazy reference? Just by a simple getter. So just as many of you maybe know the weak reference in Java, you simply would expect from a reference intermediate type like the lazy reference in general, it's a simple get method to access its contents. So and this get method will reload all content on demand. If it's already in memory, nothing will happen. It will be just returned to you. Otherwise, it will be loaded from the underlying storage. And the getter is all you have to do. There's no select blah from turnovers where ID is whatever. This is done in a background by MicroStream, because all this low-level ID stuff like primary keys or foreign keys and so on is all managed in a background by MicroStream itself. You don't have to fiddle around with technical details in your purchase. Just use your Java references as they are, and MicroStream will handle the rest. So MicroStream knows internally by an object ID mapping, which is called swizzling, every single instance which are used in an object graph is mapped to an unique ID internally. And that's done by MicroStream fully automatic, so you don't have to worry about getting the right objects back, just call the get method of the lazy reference, and you will you will get the right instance of this turnovers, and that's all. Just call a simple getter. So here see how you can initiate a lazy reference. Just say lazy.reference and hand over a new instance, or null if you like, if you have a null instance in this case, or just null it out itself. These are different ways to initiate or to create a lazy reference. A lazy itself is immutable, so you can't say lazy.set and change the contents. You always have to create a new lazy reference instead, and you're good to go. A lot of people always ask, so why do you have to use a type, a concrete type? Why don't we use an annotation, like in JPA for example? It's different reasons why we decided to use a type and not an annotation. If we use an annotation, it would be just bare Java bytecode accessing this turnovers. The library, MicroStream itself, wouldn't have a chance to intercept this call without any bytecode filling. We would have to manipulate the classes at runtime to interfere at this point, and that's where trouble begins. Hibernate has to do it to achieve the features they offer, but we decided against it because we wouldn't fiddle with the bytecode and introduce a lot of complexity at runtime, and the debuggability is hard if you have bytecode manipulation in between. And one of the other key reasons is, if we would add lazy to the values of a map, for example, so generics, it wouldn't be doable with annotations, because you can't annotate at this point. It's not possible. Java syntax doesn't allow it. So with the concrete type, the lazy type, we don't fiddle with the classes, and you can put the lazy key everywhere where you like in your model. Even if you're working with generics, you can lazy load parts of a collection, like the values of this map. And these are the two key reasons we decided to use a type and not an annotation. Alright. So, how is it done in a class? Of course, you have a field with turnovers, and the getter has to check if the turnover list is null itself, then you return null, or call the get. Now it's a bit inconvenient, I'd say, to add the null check of this. So we just provide a convenience method, say lazy get, and hand over the reference, and the null check is done internally, so you can hide the clutter in between. What we say is best practice for lazy references is to keep them internally in your API. Don't expose them to the API user. So the user of your entities doesn't care about lazy loading. He only wants the data, so keep the lazy intern, don't expose it to the outside, and you have full control, and the user cannot fiddle with it or create errors of some sort. And that's the best way, just keep it intern. Yeah. Yeah.
Okay, so you don't do that automatically.
We don't do that. Yeah, we have a few side projects by different users. So if you have a framework you're using, there are different frameworks which generate code, like getters and setters and so on. There are a few popular or not so popular frameworks out there. There are efforts for extensions where the MicroStream code can be injected by a generation time. That's possible as well, but it has to be in the compiled code in some way, of course. Yeah. Alright, the lazy get is simple, and set just creates a new lazy reference and injects the code into, or sets the turnover list newly with a lazy reference. And that's all you have to do to define a lazy loading point in your object graph, and you can do it in any point, subtypes or subgraphs where you want lazy loading. The lazy has a few different key methods, like we have seen the get method, checks if it's loaded and loads it on demand. The lazy peek returns the actual state without loading it, so it can return null. And the lazy clear will remove the reference out of the Java heap and free up the memory. And that's a very important point to consider. If you have a huge database, bigger than your RAM, you have to work with lazy loading not to run into out-of-memory errors, of course. So how is it done? Do I have to check every time, is my memory full? Do I have to unload some lazy stuff? You can, if you will. But by default, a lazy reference manager is running in the background and clears up all the least used lazy references automatically out of memory, depending on a certain memory quota. So if your memory runs over 75%, for example, the lazy reference manager gets active and clears out all least used lazy references out of your memory. You can define different approaches how the lazy reference manager should work, but by default the basically hot data is kept in memory because it's accessed more often, and the cold data gets cleared out, so you don't run into out of memory problems. So this lazy reference manager is created by default, is started by default when an embedded storage manager is fired up, and shut down when a shutdown of the storage manager is called. So we have to, in a default setup, you don't have to worry about it. But if you have special needs for the lazy stuff, you can, of course, exchange it and customize it. So that's basically how MicroStream keeps the hot data in memory all the time, because it's just simply accessed more often than the other lazy references. And this is, I would say, sufficient for most use cases. And of course, it's highly customizable, so you can do whatever you need. Alright, so now we have seen how the load data define lazy loading points, and that's it. That's all you have to do to load data. No queries, no complex joins, whatever, no primary keys, no foreign keys, just simple Java code, and MicroStream will do the rest in the background. So what about storing data? Of course. Key sentence to remember: what you have to you have to store what you changed. So in a relational database, for example, if you do an insert in a table, if you want to add an object, you say insert. With Java, if you insert an object into a collection, what you actually changed is the collection itself. So you have to store the collection, and this is one point to remember. Always store the object which is changed. So if you change the root reference, of course, there's a store root method, and storage will be basically exchanged, the whole storage, the whole root. If you add, if you change a property of virtual, like for example, name of a customer, just store the customer, because what you change is the customer itself. You changed a property of the customer, store the customer. If you create a new item and it gets added to the list, it's not enough to store the new item. You have to store the list itself, of course, because you changed the contents of the list. And don't worry if this list already contains millions of items and you add one item and you have to store the list. It doesn't matter. MicroStream knows all the remaining items are already in the storage and just will store the delta, the newly added item. But the list itself has to be stored anew to reflect the change in a storage layer. So every store operation is an atomic all or nothing operation, similar to a database transaction. So it only will reflect in a storage if everything worked out well, if only and if the response from the binary storage from the hard disk or from the blob store is positive, then the change will be reflected in object model at the next startup. So you can't create a inconsistent object graph because of some I/O error or hardware error, because only on a positive feedback from the binary storage MicroStream will create a successful transaction. Yeah. Basically, you can serialize every object there is, with a few exceptions, of course. MicroStream is based on an own newly written serializer. We don't use the built-in Java serialization out of several reasons, mostly because of security issues, and the key feature of the MicroStream serialization is it's highly customizable, and you can store and restore parts of the object graph, and that's where the storage is based on. And of course, there are some types like, let's say, a stream, a socket, or a thread, which represent external state. You can't serialize it. It's blacklisted inside the engine, so you can't run into errors. And there are several types which are not used normally in a business application in your object model. MicroStream can run into issues, of course, but you can provide custom type handlers for that, and I'll show it later on how to do it. And you can circumvent maybe some issues which will be coming later on, but in these rare cases, define a custom type handler and you're good to go, I'd say. Yeah. Alright, so every single store is a transaction, like I said. So it's basically connected to an I/O operation, and its I/O operations are expensive. So what to do if you have bulk updates on several objects and you want to pack it into one I/O operation? There's a store all method where you can hand over multiple objects, and all the different stores are packed into one operation, and so you can bulk update your storage as well. So these store methods, like I said, are transactions internally and basically are shortcuts for this code. First, a lazy storer is created, all the objects are registered at the storer instance, and a commit is called. This is done if you call a store method of any sort. Any store method you see here will call this code internally. Storer is created, changed objects are registered, and a commit. So the lazy storer is the default. What does lazy storer mean? Lazy store says every new unknown to the storage object will be stored. Every known object will not be stored. So let's say I have a customer which is already stored, and I change the customer's name and I store the customer. And every object which is referenced by the customer, and a string of course is a reference, will only be stored if it's new. If it's already there, the storage will stop at that point in a graph and dismiss the rest. So every time you use the lazy storer, the default case, you have to know what's changed. In most cases in your business code, of course you will. You change the stuff in your code so you know what's changed, and you can call an optimized store. So the least needed amount possible will be written out. So the I/O operation will be kept small. In some rare cases you don't know what's really changed because you hand over some external logic or whatever, and therefore you can use an ego storer, and the ego storer will just write all the complete objects you hand over anew, and you're safe that the changes are reflected in the underlying storage. But for the most common cases, you know what's changed because you write the code for it. You can use a lazy storer. Yeah. Yeah, that's one of the points later on. Yeah. All right. The stuff which is in memory is the object model. So if you call setters or change fields, it's already changed in memory. And what this commit does is reflecting these changes in your RAM, in your heap, in a JVM, down to the binary layer. Yeah.
So does when you store, is it like asynchronous? So do you wait for example, if you have S3, you have a response time. I don't know how much time it is. Does it wait for that?
Yeah, it's blocking. The default API MicroStream is blocking. If you use this code and put it into reflective code or in reactive code, for example, you can make it a non-blocking, of course. We did it with different frameworks where the code is used inside non-blocking stuff, and you can use it in a non-blocking way. But the default case, and in my eyes the most common case, is that you need a blocking call. You have to wait until the object is stored or available in memory. You don't have to query all the time. Is my object there already? You just wait until the method returns. Yeah. Alright, this is our eager storer is created. Just use the creation method, store your stuff and commit, and then you can use an eager storer. Different ways of customizing, of course, can be used. It's called a persistence eager storing field evaluator. It's a clunky name, but what this thing does, it evaluates all fields of a class, and every field which should be treated eager is stored every time, even by the lazy storer. So let's say we define an annotation, and the evaluator checks the annotation on the fields. You just write add eager over every field you want to store. If a customer gets stored, you write eager over the name, and the store on the customer happens, the name gets stored anyway. So you can define eager storing points in your object graph. And that's one way to customize this behavior. Yeah. Doesn't matter. Lazy is for loading, and eager storing is for storing, so that don't interfere. Yeah. Yeah. No, because if it's not loaded, it cannot be changed. So easy. Yeah. Yeah, some recap. The field evaluator, if you call the default store, which is lazy, the field evaluator is used, and if you create an eager storer, it's stored eagerly anyway. Okay. What about transient fields? If you want to leave out fields from the persistent layer, the default transient keyword is used, like in Java itself. By default, you can change it as well to, and if you want to use an annotation, you change the evaluator of the field, but the default setting is every transient field will not be stored, will not be reflected in a binary layer, and it of course can be used for flags or temporary stuff, computed fields, for example, and so on. And so you can skip fields from the storage. Example for customizing, you define a custom evaluator again, for example with a naming pattern. Every field which starts with an underline in its name should be transient, and so you can change out the behavior if you like to. So what about deleting data? In a database, if you want to remove stuff, you just fire up a query, delete from blob where with a condition, and everything will be removed. So But how's it done in an object graph? Can you really remove an object? Delete an object? Not really, no. So you have to dereference it. The object is kept in memory by the Java garbage collector as long as one reference exists to this instance. So, and if you remove all references to this instance, the garbage collector will clean it up finally or eventually. So, and that's the same with MicroStream, because MicroStream reflects the state of the JVM in a storage layer. So let's say if you remove an item from a list, what do? You change the list, so store the list again. And MicroStream has a garbage collector on a storage layer and checks the references. And if this item isn't reflected or referenced anymore by a different entity, it will be removed by the storage eventually by the garbage collector at runtime. It behaves at the same way the JVM garbage collector does. It checks references and cleans up the storage in the background, and so the storage will be kept at a minimum needed size from time to time, depending how much time you give the garbage collector or the housekeeping in MicroStream. And that's how you delete data from the storage, just like in an object graph, and it will reflect later on in a storage as well. And again, no need to call delete from where ID something. It's done in the background. MicroStream knows its IDs, which is mapped internally, and knows when an object isn't reflected anymore in a storage, and the garbage collector will take care of the deletion itself. So that's a CRUD wrap up of MicroStream. Pure Java. Do whatever you like. So MicroStream, it should store the stuff, and that's it. And it's loaded on demand with lazy loading, and this is how you do CRUD with MicroStream. Simple as that. So, a bit of customizing. Let's say the serialization in a background. It creates binary state out of memory. In most cases, our generically generated type handlers. A type handler is responsible for creating a state from a certain type into binary form and back. Let's say a type handler example for a customer, or a type handler for array list, and so on. And we have a lot of type handlers optimized for the most commonly used types in a JDK, all the collections, all the local date or time API types, and a lot of more. And the rest of the type handlers is will be created generically. It's your approaches are analyzed in the background by reflection, and the type handlers are created accordingly by default. So, but you can take control over the storing and loading process of specific Java types if you want to optimize the storage behavior, if you want to shrink the storage data or obfuscate it, or if you want to encrypt it, or whatever reason, you can write custom type handlers for that. You can define the binary representation of a simple or of a specific type, and how the state of the type will be restored. Yeah, of course, main reasons to optimize performance, of course, and the memory consumption for complex objects. So these type handlers are defined externally for arbitrary types, unlike in the Java serialization, because in the Java serializations and in JDK, in order to customize the serialization process, you have to override some magic method in the project itself in order to get it to work. So problem is, if you're not the owner of the code, let's say you want to customize the serialization behavior for an array list and type in a JDK, you can't change it. You only have the classes, not the source. It's not possible. That's why we decided to use external type handlers, and you can add it to your configuration, to your foundation of the storage, and then it's used for any type. Even if you use third-party libraries like, let's say, Eclipse collections or Google Guava libraries, you can define custom type handlers for that. Let's see it in an example. given a time slot clause, it's just a slot number and a start and end time. So the generic type handler of MicroStream will see it as 3 records in a storage, because these are 3 objects in a storage. You have the time slot itself, the int is a primitive type, is just a value in the memory, and the 2 start and end local date times are new instances of objects. So the output in a storage would be look like this. 3 records for a simple type like that. MicroStream does it by default to keep the referential integrity intact, of course. But if you say this start and end instances of the local datetime, these are just values and don't care about referential integrity, then you can write a custom type handler for that and store simple values, like let's say the timestamp of the start and end as a simple long. And then you can shrink down the binary form of this with a custom type handler, and so you see you can save, let's say, 60-70% of memory in a storage layer and speed up the loading process, of course, because you don't have to read as much bytes. So how is it done? One of the ways is to inject code into your type, if you own the source, of course. If you don't own the source, you have to use an external one, like I said before. But this is a simple case. You just define provide type handler methods with returns, which returns a binary type handler. They are factory methods, and all you see is for every field for this int, the long of the start and the long of the end. They are factories where you store the state and restore the state of this field. You create, basically you are creating primitive values out of complex values. And that's how it's done with factories inside your code. Or if you have to use or want to use a custom type handler, an external type handler, because you don't own a source, you just create a new class, extend from predefined type handler types. In this example, we want to use or create a custom type handler for buffered image. How images are stored, yeah, they are encoded to a certain format like JPEG or PNG, and that's what we want to do in here. We just use the image IO library, create a PNG encoding out of this image, put it into a byte array, and we store the bytes by the store bytes method. So that's how you create a type handler for any type you like. In this case, one from the JDK. You define the binary representation in the PNG for images, and you restore the buffered image in a different methods, but it's simple. Convert to bytes, restore from bytes, good to go. Only for the collection. Yeah. The content itself are probably different types, so different type handlers will jump in. Yeah. So, and now, what do we do when types change? Your classes evolve over the time of the life cycle of your application. So, we have to take care of it. Let's say, contact, yeah, fields move. They get renamed, new fields are added, or we want to change the content. We want to change, let's say, a string to an integer or whatever. So how do we do it? MicroStream provides a technique called legacy type mapping. The most common changes can be detected by the heuristics of the engine itself. So if you have names of fields which don't differ too much, MicroStream can say safely, there's a rename, or the field was moved because the name stayed the same, but it just moved in a class. Or if a newly added fields comes in, MicroStream can detect the most common cases and say safely, I will create a custom type mapper internally, and you're good to go. So, but if you have different cases or more complex cases, let's say you split the field name into first and last name, because you thought one name field is enough, but now you have to split it for some reason. MicroStream can't know that out of the box, so you have to define a custom type mapper for this. Just say you split this thing and fill the fields, and you're good to go. So the thing is, at the type mapping, you don't need to rewrite the whole storage if you change your classes. That's not necessary. MicroStream will do it on demand when the instance of this object gets loaded into memory. Then the type mapping happens, not before. And only if you store the object again, the new state of the object with the current class will be written to the disk. Otherwise, it's only done on demand. So the storage has to be written every single time you deploy a new version of the software, because that would just be too slow if you have several gigs or hundreds of gigabytes of storage, and every time you have to rewrite the whole storage. That's not necessary. Every case can be covered, and you can provide different type mappers for every single case there is. You can customize it down to the last byte if you like. So you can handle every single change. Yeah. There are special type handlers for that. So you don't define a type handler for the serialization, you define a type handler for the mapping process. And the code is basically the same. Yeah. If you're certain that no old version of your instances are in a storage anymore, you can remove the handler, yeah. But I wouldn't recommend it, because maybe you forgot one and you break your application because the old state couldn't be loaded. So just leave it in your code, it doesn't harm you. Yeah. Yeah. Yep, exactly, because there's not only one change, you have multiple changes over the time, so you have a history of the type. And MicroStream itself sees every version as a different type, and you can map these versions from one to another, yeah. Or every change from one to another. Yeah. Alright, so yeah. You lose data, I'm afraid. Yeah. But you can write tests for it, and so you can bulletproof it. Yeah. Basically, yeah. So I'm running out of time, I see. So I go to the rest of the slides, and if you have more questions, we at our booth. All right. So of course, backup is a big thing. You can define a continuous backup and a full backup. Continuous backup meaning you have a second binary target which is written in parallel to your original one. And a full backup just makes a copy of the storage to a different target. By default, the continuous backup is disabled, so if you enable it, a second storage target will be written. And last but not least, the housekeeping. It takes care of remove of the old data, like dereferenced objects, which are swept by the garbage collector at some point, and the defragmentation, because MicroStream writes data at the end of the files. It never overwrites data to avoid corrupted files, and so you create gaps with old data, just a fragmentation of your files, and the housekeeping process in the background will defragment the files in the background, and this stuff can be called by hand. Yeah, covered the garbage collector already, and you can define the time slot, the budget for the housekeeping. If you have a write-heavy application, lot of new data coming in all the time, maybe IoT or sensor data or whatever, I would increase the housekeeping time so your storage can kept clean in a more in a faster way, so your storage doesn't grow exponentially. Alright, so you can call all the housekeeping tasks by hand, the cache check, file check, and so on. It's maybe too much, and for my time to go into every single one of them, but they are good. They are documented, and the API docs say what they do in detail. So MicroStream itself is on GitHub. Or the project is open source. The docs are reachable by docs at MicroStream 1, and like you heard probably by now, we are moving it to the Eclipse Foundation. The MicroStream project itself is split into two: the Eclipse serializer and the Eclipse store. These are the project sites and the repos at GitHub. EclipseStore.io is the new top-level domain, and the first snapshot was released last week. So the manual is at GitHub site, and these are the coordinates for the snapshot in a Sonatype repo. Like I said, two projects, the Eclipse serializer and the Eclipse store, in a version 0.1 snapshot. The final release will be probably in September, because we have to follow the foundation's process for the first final release. But this code in September will be the version alike to MicroStream 8.1, and from there on we will go forward at the Eclipse Foundation, and MicroStream only will be patched backwards. So update your favorites in time. Alright, thank you for joining, and if you have any more questions, please follow me to our booth, because the next talk is coming, so we can answer all of them. Thanks.